Hello and welcome to our introduction to Chapter 5, Chemical Bonding. In this chapter, we are going to start building up our covalent molecules, things that have shared electrons. So we're going to be looking and focusing on our nonmetal section of the periodic table, and how do those nonmetals form bonds? How do they share electrons? We know that the sharing of electrons occurs in order to reach a stability, a noble gas electron configuration. But now we're going to be able to say, well, if this molecule exists with this specific molecular formula, what does it look like? All the way to from the connections through to the molecular shape. Now, this guy. I think he's amazing. This is Linus Pauling. Linus Pauling, an American chemist. Yes, he was a biochemist as well, and a chemical engineer, and a peace activist, and an author, and an educator. He had it all. I think he's phenomenal. I also think his smile is contagious. He had written more than 1,200 papers and books, which dealt with over 850 scientific topics. This is phenomenal. He is one of the founders of quantum chemistry and molecular biology. He was born in 1901 and he died in 1994. And one of his most important contributions was his book, The Nature of the Chemical Bond. He noticed that there was a difference between these single bonds in terms of how much energy was released when they formed. So he studied what we call bond energy. We will get into a good definition of bond energy and what it does, but it has to do with the amount of energy released when a bond is formed. The bigger the number, the more stable the bond is. And so what he looked at was he compared the numbers of H2, hydrogen diatomic, and F2, fluorine diatomic. And he looked at these two numbers and he said, you know what? I'm going to predict that if a covalent bond is an electrons pair being shared, these are both single bonds, 2 electrons are being held right here, 2 electrons are being held right here, that he predicted, or what was predicted at the time, was that the bond energy of HF would be exactly average, 296 kilojoules. Linus Pauling did the work and discovered a very remarkable outcome. That is not related at all. The bond energy, the amount of energy released when HF forms, is 565 kilojoules. And so what he started to say and predict was that HF has some ionic character. And that there is something about the electron attraction and the electron repulsion going on in HF, and he'll start to call this polarity. Now, polarity is going to be a very, very big topic for us in chemistry. Now, bond polarity. Most bonds have some degree of sharing when they are covalent bonds, and some degree of ion formation in them. So in life, we're not black and white. We're not just ionic or just covalent, and it's just one thing or the other. There's a very gray area of degree of ionic or degree of covalent. Bonds are classified as covalent if the amount of electron transfer is insufficient for the materials to display the classic property of ionic compounds. So just because we label something ionic and we say that typically that's a metal and a nonmetal, that doesn't necessarily mean that there is an equal sharing of electrons. There's not enough energy to transfer the electrons fully, but there might be some degree of transfer. So if the sharing is unequal to produce the dipole or the actual ions, right? Think about those little magnets, the plus charge and the minus. If there is an unequal sharing to produce the dipole, it starts to look like ions. And instead of classifying it as ionic, we're gonna start classifying it as polar covalent. So it might look like ions, but we'll still be able to say, yeah, it's covalent, they're shared, but they're not equally shared. One atom holds the electrons tighter than the other one does. So in covalent bonding between unlike atoms, that results in an unequal sharing of electrons, that usually means one atom is pulling the electrons closer to its side. That means that that one end of the bond has a larger electron density. So that results in the polar covalent bond. The bond is polar. It will have a partial negative and a partial positive charge. We'll be able to see what that looks like on the next slide. What I wanted to get into just briefly is that idea that if an atom pulls the electrons more, let's just say atom X versus atom Y. And let's say that atom X likes the electrons more, and so they start shifting over to him. Atom X is going to have a partial negative charge. That partial negative, again, isn't a full negative. It's what we call a delta minus. Delta is that lowercase d, Greek letter. It just means that the element X must like electrons more than element Y. Element Y is feeling a little bit electron deficient. It's not getting its full octet. It's losing a little bit, and that's what we call a partial positive. So this is important, especially for organic chemistry and biochemistry, when you start getting into reactivity. We won't see reactivity at all in this unit, but what we will be able to do is look at a molecule, identify whether the bond is polar covalent, and identify which end of the bond has a larger electron density, who holds the electrons more. That would be the partial negative side. And then who is electron deficient, who has the partial positive side. So it's all about identification for us. Now, electronegativity is a much better periodic trend. It kind of takes over for electron affinity, right? Remember we talked about electron affinity being really weird and wonky and saying that there really was no trend going down a group. Well, now what Linus Pauling was able to describe and to plot out for us is a unitless value that explains the idea of electron attraction. The higher the electronegativity, results in an increased attraction to electrons. That means that the atom would want the electrons more. The element that we see that has the highest electronegativity is fluorine. If we zoom in on this chart, the periodic trend you should know. You should understand why this occurs. So we're going to dive into a little bit of periodic trends again, just specifically focusing on electronegativity now. So if we look at fluorine, he has the highest electronegativity on our chart, 4.0. Again, unitless value. The higher the number, the more likely that you want electrons. So electronegativity, the ability of the atom to attract bonding electrons to itself. That's what we want to be able to see. The larger the number, the more likely that atom wants electrons. Now, the larger the difference in electronegativity between two atoms in a bond, the more polar the bond is. And so what we actually get to start to calculate is the change of electronegativity between the two nonmetals. The more difference that is, the larger the value. It will be an absolute value. We're not going to look at positives or negatives. Just take the biggest one minus the smallest one and say, what's the difference? The more likely that bond will be identified as polar. leading towards the actual ionic scale. So we can look at this. This would be between H and F, the molecule that Linus Pauling was looking at. The electronegativity of fluorine is 4.0. The electronegativity of hydrogen is 2.1. So that change in electronegativity, 4.0 minus 2.1, again, biggest minus the smallest, 1.9. And what we see here is that fluorine has the delta minus, hydrogen has the delta plus. We can draw this dipole arrow. It always points towards the atom that has the delta minus, and it has this little positive symbol down at the other end where the atom that is electron deficient, who has the delta plus. Electronegativity and difference in bond type. If the difference of electronegativity is 0, equal sharing, so things like H and H, H2, the change in electronegativity there is 0 because those two atoms are identical. That is what we call pure covalent. Now, if the difference between electronegativity is somewhere between 0.1 and 0.4, the bond is not polar enough to see any sort of uneven sharing of electrons, so we call that non-polar covalent. The typical example will be carbons to hydrogens. Carbon is a 2.5. Hydrogen is a 2.1 in electronegativity. So overall, their change in electronegativity is a 0.4. That's what we call a non-polar covalent molecule. That would still lie in the idea of equal sharing of the electrons in the atom. Now, if the difference of the electronegativity is between 0.5 and 1.9, that's what we describe as polar covalent. That is something like HF, or even HO. Oxygen, if we look on that electronegativity chart, is 3.5. Hydrogen, again, 2.1. That difference, 1.4. Polar covalent, unequal sharing of electrons between the atoms in the bond. Now, if the difference between the bonded atoms is larger than or equal to 2.0, that's what Linus Pauling defined as ionic. And so when we look at this idea of metals and nonmetals, we start to see that it's not the best definition of bonding. This is a more accurate definition of bonding, looking at the actual desire or the ability to attract electrons in a bond and say, is there enough change in electronegativity to transfer electrons, or just to provide an unequal sharing, or just to provide a perfectly equal sharing of electrons. Now, writing Lewis structures. This will be one of the most important processes that we do in this unit. If you do not understand or struggle with Lewis structures, you will struggle with the rest of the unit in terms of identifying what the molecular structure looks like in three-dimensional space. So what we do want to do in writing Lewis structures is follow a couple of steps, a guideline, if you will, or a process in order to be successful. The first thing that we want to do is predict the skeletal structure from the molecule formula. So you will always be given the molecular formula, and you want to predict what is happening. The best question to ask yourself is, which atom goes in the middle? Which atom is the central atom? To answer that question, what we want to be able to say is, who makes the most number of bonds? Now, we know from what we decided from Lewis.atoms is that carbon makes more bonds than nitrogen. Nitrogen makes more bonds than oxygen. And then oxygen makes more bonds than fluorine. As we look at the number of valence electrons, as valence electrons increase, the number of bonds decreases. So we would never really want to put fluorine in the middle when we could put oxygen in the middle. The second rule that we want to be able to do, once we start predicting who's in the center and getting some sort of idea about the structure based off of what we know in bonding, we need to calculate the total number of valence electrons. Now we only want the valence electrons because those are the ones that go into bonding. We don't need core, we just need the total valence electron count of all the atoms provided in the structure or in the molecular formula. Then we want to be able to distribute those valence electrons, giving out octets if we can to outer atoms first. Why we want to do outer atoms first is just a little rule of thumb. You know, you can do whatever atom you want, but we want to try to get the octet first because what we'll start to be able to see is that the central atom will be able to dictate if they need any double bonds, triple bonds, or if everybody's just a single bond. The last couple ones that we have, again, give double and triple bonds. If necessary. We'll identify what that means, and then we'll do a check. We're going to be able to say formal charge here. We'll learn what that is. And resonance. We'll learn what resonance means. We'll start with looking at simple Lewis structures that really only need numbers 1 through 4, and then we'll get into the more strict Lewis structures that require number 5. So here's our first molecular formula. We're going to start with CH4. So predict the skeletal structure. Which atom is going to go in the middle? And we will always have one central atom for our discussions in this class. Yes, you can build up and get more than one central atom. We'll get there, but not right now. When we look at CH4, what we want to be able to say is carbon makes the most number of bonds, so I'm going to put carbon in the middle. Hydrogens then would go all around the outside. Now again, Lewis, simplification. Just put them somewhere. We're really just getting connections here. That's step number 1. Step number 2, count up the valence. Carbon brings 4 electrons to the table. Hydrogen brings 1, but there are 4 hydrogens. So that's a total of 8 electrons. Wonderful. Step number 2, done. Step number 3, start to distribute these 8 electrons. Now when we distribute, we want to do 2 electrons at a time. The reason for that is because electrons pair themselves, 1 from each atom. Now what Lewis did was he understood, yes, I'm grouping all of these 8 electrons together, but when I distribute them as pairs, that really understands the idea that 1 electron from each atom is coming together to be shared. If I put 2 electrons together and I want to call it a bond, we draw it as a line. There are 2 electrons here between carbon and hydrogen at the top, 2 electrons being shared between carbon and hydrogen on the right, 2 at the bottom, 2 on the left. There are 4 single bonds. 1 to each, carbon to hydrogen. Lovely. Now, here's what I want to say. Do I need to do double or triple bonds? Well, I've distributed all my 8 electrons. Check. Does everyone have their octet or their duet? That's what we want to be able to say. Hydrogen needs a duet to reach its electron configuration, that of helium, with 2 electrons in the 1s orbital. And carbon needs an octet. So let's go ahead and double check. Hydrogen, 2 electrons. Yep, everybody's got 2. Carbon, 1, 2, 3, 4 bonds. 2 electrons in each, 2 times 4, 8. Lovely. Everybody's set and ready to go. Let's do another one before we get into exceptions. CH2O. Now, who's going to be in the middle? That's carbon again. This time we'll have oxygen, hydrogen, and hydrogen. Again, just put them around. Give them some room. If you even want to say, hey, can I spread these out even more? Sure, of course. Why not? Give them as much room as they need, right? So that your structure looks clean and not really messy. All right, count up those valence electrons. 4 from the carbon, 6 from the oxygen, and 1 each for the hydrogens. 12 electrons total. Let's go ahead and start distributing. 2, 4, 6. Now, when I want to do my distribution, number 3, to the outer atoms first, I know that I've done 6 electrons in my bonds. So I have 6 electrons left over. Both hydrogens have their duet. Now let's focus on oxygen. 2 electrons can be put in as a lone pair. It's to fill the oxygen's octet. 2 more, 2 more. Now that oxygen, let's count up the electrons it has around him. 2, 4, 6, 8. Wonderful. We have the 8 electrons around oxygen. So we've distributed, again, we've also distributed all of our electrons. We distributed 6 more. So if we were to count 2, 4, 6, 8, 10, 12 electrons total in this molecule. But let's look again and say, now we have to move to number 4. Do I need to give double or triple bonds? Well, the only way to answer that would be to say, does everyone have their octet? No, carbon doesn't, but I don't have any more electrons to give. So instead, what I have to do is I have to get rid of 1 lone pair and share it between the oxygen and the carbon. So what that means is that the oxygen and the carbon has what we call a double bond. Hydrogens to carbons are going to be single bonds. And when we look at what's left over on the oxygen, these are our non-bonding lone pairs. They are not bonding because they are not held between 2 atoms. They are solely on the oxygen and only the oxygen. That one's gone. I like to erase it and to make it all clean at the end of the day. So we can start to see how carbon can now make a different type of bonding. 2 single bonds and 1 double bond. But what we identify at the end of the day is that carbon still makes 4 bonds.